Have you ever wondered how engineers actually track and measure a computer crash? They use a specific set of rules to turn a chaotic breakdown into a map they can follow. Imagine a long, carefully lined up row of dominoes. Right in the middle of the line, one piece is sitting slightly crooked and wobbly. Engineers call this wobbly piece a fault. In software, a fault is usually a human mistake resting quietly in the background. Think of a tiny typo hidden deep inside thousands of lines of code, staying completely hidden until the right moment. That hidden typo stays harmless right up until someone runs that specific line of code. At that moment, our wobbly domino finally tips over, striking the pieces next to it. The pieces falling into each other represent an error. The computer's memory is now in an incorrect state, and that bad information is actively spreading from one part of the program to the next. At the very end of our domino line is a beautiful toy castle. The falling dominoes slam into the walls, collapsing the towers and ruining the structure. This is the final system failure. This diagram shows a server rack running perfectly, and then suddenly flashing red alerts and stopping all data flow. That ruined castle is the same result you see when an application stops delivering its service to you. A server going down is a predictable three-step chain reaction: a fault, causing an error, resulting in a failure. To fix these failures, we first have to figure out exactly how the system broke. At the testing station, we have 3 toy robots that show the different ways things break. Our first walking robot is doing fine until its battery unexpectedly disconnects. It stops dead in its tracks and freezes completely still. In the tech world, this is a total freeze. It's what happens when a server simply shuts down or an application goes completely offline without warning. Next, look at this toy mail truck. It is still driving its normal route, but letters are continuously spilling out onto the floor. This is a silent drop. The server stays online, but it's failing to catch the important messages it is supposed to be receiving, like a letter falling out of a truck. Finally, we have this third robot. It hasn't stopped, and it isn't dropping things. It's spinning wildly out of control, spraying purple paint everywhere. This is the most difficult kind of breakdown because there are no rules. The system is behaving in a completely unpredictable, chaotic way. Because there is no logical pattern to the purple paint spraying everywhere, these chaotic breakdowns are the hardest problems for a team to diagnose and fix. Once you know your system froze, dropped its messages, or went chaotic, you know exactly which tools to pull from your workbench to fix it. Now we need a way to measure the time between these crashes. Let's head over to the miniature racetrack to see how engineers track these timelines. Watch this toy race car. It is zipping around the track, completing lap after lap smoothly without a single hiccup. This chart shows a solid green timeline, representing healthy uptime. This phase is the average amount of time the system runs perfectly before a problem eventually pulls it off the track. Suddenly, a tire blows out, the car skids into the pit stop, and a tiny crew of mechanics immediately rushes in to perform repairs. Our chart updates with a short red bar. This repair speed measures how fast the crew gets the system back into the race. Adding healthy uptime and repair time together gives the full cycle. This is the total time from one breakdown to the next. By tracking these specific time cycles, engineers can predict future crashes and build highly reliable digital worlds. Next time, we'll look at keeping the race going even when a car breaks down.